We're going to be around a long time. As long as there's airplanes flying, the TDT will be here.
NASA Langley Research Center in Hampton, Virginia is famous for its world-class wind tunnels and wind tunnel testing techniques and methods. One of those tunnels provides a very unique type of testing. It's the Transonic Dynamics Tunnel, or TDT. Since 1960, the TDT has provided an unequaled capability for aeroelastic testing. It may well be the best facility in the world for studying a full range of aeroelastic phenomena at transonic speeds.
Well, aeroelasticity is the interaction of structural forces, aerodynamic forces, and inertial forces. It's the elasticity of the wing. You know, it can vibrate. You've got the aerodynamics of the wing that's flown over the top of it that's creating some interactions, and then you've got these inertial forces which tend to make things vibrate along with the structure.
It's the study of how aerodynamic forces on a vehicle interact with the structure, and how this interaction influences the design and performance of flight vehicles. Modern aerospace vehicles are designed to have structures as light and efficient as possible, while still being able to withstand the loads encountered during flight. Problems occur because an efficient structure is usually flexible, and that flexibility is at the heart of dynamic aeroelastic phenomena. The TDT has been used to test many types of aerospace vehicles, including most active commercial and military aircraft, as well as helicopters, tilt rotors, parachutes, spacecraft, ranging from launch vehicles to planetary landers, and a wide range of generic research models. Although it's over 40 years since the tunnel became operational, the TDT has continually kept pace with advancing technologies, and its capabilities remain state-of-the-art. Before 1960, another tunnel was located where the TDT stands today. The 19-foot pressure tunnel came online at the beginning of World War II. It was the first attempt anywhere to combine large size and high pressure in one facility, and it could test large-scale models at speeds over 300 miles per hour. But by the early 1950s, the jet age arrived, and its lack of high-speed capability made it obsolete.
For the higher speed airplanes, the wings became thinner and more flexible, more susceptible to flutter, and they were flying at transonic speeds where the aerodynamics was complex and very difficult to predict.
Since none of the existing tunnels had the right combination of capabilities, the researchers used various methods to try to investigate the phenomena. But the methods were often unreliable, ineffective, and usually expensive. The lack of a suitable facility eventually led to a proposal: a large transonic wind tunnel dedicated to aeroelastic testing. Such a tunnel would have to meet a number of requirements: be as large as possible for the accurate simulation of model details, be capable of operating over a wide range of density to simulate various altitude conditions, be able to operate at speeds up to 1.2 times the speed of sound, and it must be able to use Freon as a test medium.
Freon is a gas, it's non-toxic, it's invisible, but it's much heavier than air. And so it makes it very nice in making a model.
This allows us to build wind tunnel models that are heavier than if we were testing an air medium. It also gives us special properties such as the speed of sound is half that of air. The frequencies that the model vibrates at are lower, so when we test our aeroelastic models, the motions are actually at a slower speed than they would be for a model scale for air testing, which makes it a little bit safer for us to test the models.
The answer? Convert Langley's 19-foot pressure tunnel. The design and conversion process took about 6 years and almost $10 million to complete. At today's prices, this same tunnel would cost more than several $100 million. The first opportunity to show what the tunnel could do came during its first year of operation.
At that time, 1960, the Transonic Dynamics Tunnel was just coming online. It had never done a test in anger, if you will. It had been calibrated, but it was sitting there waiting for a problem. And this was a big problem.
After 2 unexplained fatal crashes of its new turboprop Electra and several mysterious incidents of severe vibration during flight, Lockheed and the FAA approached Langley and its new facility to help find the problem.
The interesting thing is, the whole aviation industry was concerned about this problem, not knowing what it was in the beginning, and they wanted to understand it.
Evidence gathered from the crash sites and stories from passengers and flight crew pointed to a strong possibility of flutter.
One day at a conference in Burbank, there was only about 5 of us sitting around the table. And one of the Lockheed engineers said, "I wonder if it could be whirl flutter." And he's the one that proposed it.
Eventually, the team discovered that during flight, the aeroelastic phenomenon known as propeller whirl flutter could occur if the engine housing was weakened by excessive loading from turbulence or hard landing. Researchers and engineers from Langley, Lockheed, and Boeing had solved the mystery and saved many lives in part by using the TDT. Although initially there had been a lot of debate on whether the TDT was a worthwhile investment, helping to solve the Electra problem established the tunnel as an extraordinary facility and one that restored public confidence in flying.
I think we really made right much contribution fixing that airplane. And I know some people said, look, if you don't, at that time when we finished with Electra, we were told, said, look, if you never do another thing with this tunnel, you've already paid for it.
From that time on, this tunnel, the Transonic Dynamics Tunnel, has been used in the development of virtually every military high-speed airplane and civilian transport from its inception in 1960 to the present day.
The TDT is a closed-circuit, continuous-flow wind tunnel, capable of testing large models over a Mach number range from 0 to 1.2. It's powered by a 30,000 horsepower electric motor that drives a ring of almost 50 blades, up to 470 revolutions per minute. The flow first passes through a set of cooling coils that act like a giant heat exchanger to remove the tremendous heat generated during operations. It's then directed toward the test section by 2 sets of turning vanes. The flow accelerates quickly, where the tunnel narrows and the test section begins. The test section is 16 foot square with cropped corners. Because of the slotted walls and re-entry flaps located just downstream of the test section, the test section flow can reach velocities that surpass the speed of sound. Part of the floor can be raised and lowered to move larger models in and out. Downstream of the test section is another set of turning vanes followed by safety screens that protect the tunnel fan blades from debris in case of a model failure. One feature that's particularly useful for aeroelastic testing is a group of 4 bypass valves connecting the plenum to the opposite leg of the circuit, just downstream of the fan drive motor. If a model begins to experience instability during testing, the valves are opened, causing a portion of the flow to be diverted into the plenum. The result is a rapid decrease in the test section Mach number and dynamic pressure. The bypass flow is then recaptured through the tunnel wall slots and re-entry flaps, located just downstream of the test section. Today, because of environmental concerns, the TDT does not use Freon as its heavy gas medium. It uses R134A refrigerant. And like Freon, it means having better simulation of full-scale flow conditions, easier fabrication of scaled models, and low tunnel power requirements.
And this is a unique capability here in our country, and we believe it's still a unique capability in the world. The ability to test with a gas that's about 4 times heavier than air for a given volume and pressure and temperature condition.
The tunnel can operate at various pressures from sea level, or 1 atmosphere to near vacuum, to simulate extremely high altitudes and even the atmosphere of other planets such as Mars. In preparation for testing, a system of compressors pumps out air from the tunnel. If heavy gas is to be used, R134A is exchanged for the air. When testing is complete, the gas is pumped out of the tunnel, liquefied, and stored in a large tank. During testing, the test section and surrounding plenum area of the tunnel can be isolated from the rest of the circuit. A gate valve upstream of the test section is closed, and a rotating butterfly valve downstream is also closed. This isolation allows quick access to the model for any needed changes at inspections. The remainder of the circuit can stay at low pressure, even with the R134A present. Researchers can use a variety of mounting and suspension systems for their models, including a sting mount, a 2-cable suspension system for full-span free-flying models, and a sidewall turntable mount that can be set up to oscillate as well. At different times, other systems have also been used to accommodate a variety of models. A large matrix of windows next to the test section provides excellent model observation capabilities from the control room. Numerous cameras inside the tunnel provide additional observation through a set of television monitors. Besides having direct control of tunnel flow conditions, researchers can then monitor and display data captured by the highly sophisticated data acquisition system. Test personnel can view model forces, pressures, accelerations, tunnel conditions, and the output of other instrumentation on various operator screens located throughout the control room. The data can also be easily accessed at a later date. And the Data Acquisition System team is continuously developing new capabilities and improvements for the system. An additional feature of the TDT is a set of 4 vanes that can be installed upstream of the test section. These can be oscillated at various frequencies and amplitudes to simulate atmospheric turbulence or gusts. Researchers and technicians perform various model assembly and checkout activities in the tunnel's model preparation area. Connection to the TDT data acquisition system is through a large instrumentation patch panel and the local computer network. Using the same system that the control room will, engineers perform instrumentation calibration, ground testing, and computer system setup tasks. Larger models can be hoisted from this area to the shop area above.
And the models are not cheap. You know, the models can range anywhere from a couple $100,000 to 3 or 4 million.
If a model needs repair or a modification any time before or during the testing process, highly skilled technicians can perform the work in the TDT shop. Over the years, the tunnel has served as a real workhorse for experimental research and vehicle testing. Since helping to solve the Electra problem, it has continually contributed to improving the safety and performance of many aerospace vehicles through aeroelastic and non-aeroelastic research and testing. Probably the best-known dynamic aeroelastic phenomenon is flutter. It can be very violent, and once beyond critical flutter speeds, it can cause severe damage and even destruction of a flight vehicle. Flutter is a self-sustained oscillation encountered on lifting surfaces such as wings, tails, and control surfaces. The interaction of aerodynamic forces combined with the stiffness and inertia of a surface all play a part in this phenomenon. Flutter can take on many forms and generally involves the coupling of 2 or more modes of oscillation. In the TDT, significant research and demonstration testing has been performed to suppress flutter using various methods, with the promise of reducing weight and improving aircraft operation and mission effectiveness. Another dynamic phenomenon is buffet. It's a random response that occurs when unsteady separated flow passes over the aerodynamic surface of a vehicle. Or it can occur when one part of a vehicle produces a turbulent wake that impinges upon another part. Since the early 1960s, rotorcraft testing has been conducted in the TDT and has included a wide range of experimental investigations using a variety of scale models and test beds. The tunnel has made many valuable contributions to this technology and still continues to do so today. A prime example is the type of hub used for the blades of the XV-15 and the V-22 Osprey.
By putting this coning flexure in there, it allowed the blade to flex more freely, and the aerodynamics didn't have a significant effect, and we got a much higher stability boundary.
The research has also been key in the development and application of new analysis methods for rotorcraft. Through measurements made during testing, the TDT acquires unsteady pressure and loads data. This data has been most important for the development and validation of increasingly more capable and accurate computer codes for predicting aeroelastic phenomena.
A very big part of the charter of TDT right now is to provide data that helps us, validate our methodology and our codes. So I think, a big chunk of what's happening in in the TDT today is directed, precisely at computations and trying to make those computations better.
Many of the tests conducted in the last 10 years have dealt with active controls and have dealt with smart materials and controlling aeroelastic instabilities and actually exploiting the aeroelastic properties of the wing to improve aerodynamic performance.
The TDT has the capabilities to perform an incredibly wide range of conventional and non-conventional tests. Research in control surface buzz, static aeroelasticity, and various performance tests have all relied on using the tunnel for testing. In ground wind loads testing and launch vehicle dynamics testing, the tunnel is able to simulate conditions that occur during the launch of a vehicle from liftoff on the pad until it exits the atmosphere. With parachute deployment, performance, and stability tests, researchers are able to investigate how the parachutes used on interplanetary missions will function.
Very often we bring wind tunnel models into our facility that have many different parameters that can be varied during the testing. So we may have the capability of varying the stiffness of a control surface, or we may be able to change the stiffness of the vehicle through the use of a modern smart material.
A new model prep area has been completed, and a new data acquisition system is being planned, as well as improvements for the entire facility.
We are continually looking for ways to improve so that we can stay economically viable, and at the same time simply make sure that we are indeed providing a capability that the nation needs.
The TDT is an incredibly versatile facility. But what make its unique capabilities so successful are the highly qualified people who work here. From its first days of operation, the researchers, engineers, and technicians have had the expertise in the areas needed to accommodate any project. As a result, researchers have always been able to accomplish work no one ever considered when the tunnel was originally built. It's the teamwork and the dedication of this experienced staff that continue to earn accolades for the successful work of the tunnel. In the future, as new technology advances take place in flight, the Transonic Dynamics Tunnel will step up to the challenge to meet new requirements for testing. Tests performed in the tunnel will always reduce the risk and cost of aerospace vehicle development and flight testing and help to achieve the best designs possible.
This is a very unique organization here where we have theoreticians, analysts, and experimentalists all in the same branch.
We're very proud of what we do here in the TDT, and we know we have a unique facility.
This is a unique capability here in our country, and we believe it's still a unique capability in the world.
We're going to be around a long time. As long as there's airplanes flying, the TDT will be here.
NASA Langley Research Center in Hampton, Virginia is famous for its world-class wind tunnels and wind tunnel testing techniques and methods. One of those tunnels provides a very unique type of testing. It's the Transonic Dynamics Tunnel.
Thinner and more flexible, more susceptible to flutter. And they were flying at transonic speeds where the aerodynamics was complex and very difficult to predict.
Since none of the existing tunnels had the right combination of capabilities, the researchers used various methods to try to investigate the phenomena. But the methods were often unreliable, ineffective, and usually expensive. The lack of a suitable facility eventually led to a proposal: a large transonic wind tunnel dedicated to aeroelastic testing. Such a tunnel would have to meet a number of requirements. Be as large as possible for the accurate simulation of model details, interact with the structure, and how this interaction influences the design and performance of flight vehicles. Modern aerospace vehicles are designed to have structures as light and efficient as possible, while still being able to withstand the loads encountered during flight. Problems occur because an efficient structure is usually flexible, and that flexibility is at the heart of dynamic aeroelastic phenomenon. The TDT has been used to test many types of aerospace vehicles, including most active commercial and military aircraft, as well as helicopters, tilt rotors, parachutes, spacecraft, ranging from launch vehicles to planetary landers, and a wide range of generic research models. Although it's over for TDT. Since 1960, the TDT has provided an unequaled capability for aeroelastic testing. It may well be the best facility in the world for studying a full range of aeroelastic phenomena at transonic speeds.
Well, aeroelasticity is the interaction of structural forces, aerodynamic forces, and inertial forces. It's the elasticity of the wing. You know, it can vibrate. You've got the aerodynamics of the wing that's flown over the top of it that's creating some interactions, and then you've got these inertial forces which tend to make things vibrate along with the structure.
It's the study of how aerodynamic forces on a vehicle. For 40 years since the tunnel became operational, the TDT has continually kept pace with advancing technologies, and its capabilities remain state-of-the-art. Before 1960, another tunnel was located where the TDT stands today. The 19-foot pressure tunnel came online at the beginning of World War II. It was the first attempt anywhere to combine large size and high pressure in one facility, and it could test large-scale models at speeds over 300 miles per hour. But by the early 1950s, the jet age arrived, and its lack of high-speed capability made it obsolete.
For the higher speed airplanes, the wings became